And we have once again the same problem. I'm not going to read its statement or because first method is equally important as the second one, because first method is basically basics. We used basics to solve the problem in method 1, and this is method 2, and this you need to think something else. And how I'm going to guide you, just consider a coordinate system that moves perpendicular to the magnetic field. Perpendicular to the magnetic field. Just think about it. I guess magnetic field was in z direction, positive z direction. X-axis was like this, y-axis was like this, and this was the z-axis. So you need to consider a coordinate system, a new coordinate system, and that is moving, and it moves perpendicular to the induction lines, say in this direction with velocity, suppose that v0. This is your new frame, moving frame. Its velocity v0 is relative to the lab system, laboratory system, and in this frame, if the instantaneous velocity of the charged body is v, then the velocity in laboratory system will become v plus v0. Vector v plus v0 is the relative velocity of the charged particle in the laboratory system. And Newton's laws of motion can be simply written as forces acting on it will be q, velocity in the lab system, that is v plus v0 cross b plus mg vector, and that will be equal to mass into acceleration of the particle in the lab frame. And this equation can be further written as q v cross b plus mg plus q v naught cross b equal to mass into acceleration. This above equation can be written in this form. And A is the acceleration, basically acceleration of the body, which is in the laboratory system, and it is same vector as it is in the other uniformly moving coordinate system, this one, because this system is moving with constant velocity with respect to the lab system, so acceleration in both frames will be same. Now we are going to try a trick. You can see this expression, and if the magnitude of V is chosen appropriately, simply as I can suggest, you can choose V0 equals mg upon qb, and you can see the direction of V0 cross b will be in the vertically upward direction. And if you choose the velocity v0 equals mg by qb, you will see the expression in this square bracket vanishes. It becomes equal to 0. These two terms just cancel each other out. Then the equation of motion is as if the body was weightless and were moving, because in the frame of this moving observer, gravitational force cancelled out. We can also say that a homogeneous vertical upward electric field E equals V naught B, V naught cross B, in fact. Magnitude will be definitely V naught B, because B and B naught are perpendicular to each other. Is present there, and the effect of this electric field balances the vertically downward gravitational force of magnitude mg. And it is well known that in a homogeneous magnetic field, the trajectory of a particle with initial velocity perpendicular to the magnetic field lines is circular, and the particle moves uniformly along the circle with circular frequency omega naught equals qb by m. And this is also the case in the present case, since the initial velocity of the body in the laboratory frame is 0 and our frame is moving with a velocity v with respect to the laboratory frame. So the particle will have a velocity v naught, a velocity v naught in the moving system, in the moving coordinate frame, in our coordinate frame. And you can find that the radius of this circular frequency is simply v naught by omega naught. V naught equals r omega is the well-known formula in circular motion. So this is the radius of the circle in which our charged particle is moving, and we have the values of omega naught, and you can write this. The value of V naught is, of course, we have V naught equals, we just assumed V naught equal to mg by qb, and omega naught was qb by m. If you put those values together here, you will get m square by q square b square g, the value of r. Yeah, you can get. And if you visualize the motion from the laboratory frame, basically the motion of the charged particle is superposition of uniform circular motion with velocity v naught, and our observer and the coordinate frame is moving with velocity v naught. This is the motion you can observe in laboratory frame, the superposition of this, and then shape of the trajectory, the equation of trajectory you can find, or the shape of the trajectory is cycloid. In such cases these two motion merge to provide a cycloidal motion. And you can find now all the solutions very much clearly. The first part of the problem was find the maximum velocity of the object. And In the first problem, we needed to find out the maximum speed of the particle. And if you see at this picture, in laboratory frame, of course, you will eventually find that velocity of the body will be the maximum at the deepest point of its trajectory here, because both type of motions, velocities of both types of motion will become parallel to each other only at this point. And you can simply write that V max is equal to 2V0, and we already have the value of V0 mg by qb, so you will get the value maximum velocity as 2 mg by qb. This is our first solution. Then if you want to find the greatest descent of the body relative to the starting point, you can also get, and that will be equal to 2r, and the value of r we already obtained, and you can multiply it with 2 and you will get your result. So it's done again. And second and the third problem was find the average velocity of the body in horizontal direction. And the velocity of the body is vector sum of the horizontal velocity v0 and the velocity resulting from the circular motion, this thing and this thing, and it's the average velocity of circular motion is 0 because it is fluctuating around 0, and so average velocity is of course horizontal and equal to v0. You get your third result, and as a final result you needed to find out the acceleration of the body, and there is no acceleration in this frame. This frame is not accelerating with respect to ground, so due to this motion you are not going to get any acceleration at all, and so you have to look into this motion, and this is a circular motion and the uniform circular motion, so acceleration will be simply at every point v0 square by r, and put the value of v0 and r and you are going to get it g. And I think there is one more way to solve it, the third method of solution, but I am not going to provide because I am tired. Thank you very much for watching.